Okay, so malaria, there's about 200 million infections of malaria every year. They kill about 400,000 people. Researchers are struggling to come up with new interventions that are going to work against malaria in the face of the decreasing efficacy of anti-malarial drugs as the parasites develop resistance to it. Less known are things like loa. This lives in people's eyeballs. There's more than 10 million infections of this in North Africa. It was thought to be benign. It turns out it's not. But in when people have severe infections of this, the drugs that are used to combat it have severe side effects, and so researchers are trying to find new drugs to help combat this. AIDS sort of continues unabated through Africa. This is from a clinic in Benin where researchers are working with female sex workers to find out if pre-exposure prophylaxis can reduce transmission. And in all of these cases, the researchers are using things like differential equations as one of the many tools that they're using to try and capture the key components of the disease in a way that's tractable and that can be used. Okay, so this is who I work with. This is a group of about, well, not in this photo, but in general, it's about 200 computational epidemiologists. They work on a huge range of diseases, both in a completely academic and a completely applied context. They're terrific people. But what they don't want to do particularly is write a lot of code. They want to work as close to the mathematics and the things that they want to model out as possible. So that's where I come in. I'm a research software engineer, and I'm part of a group of research software engineers that we're lucky to have at Imperial College London. There are currently 6 of us, ranging from web developers through to people who are ex-computational biologists. Okay, so a lot of the work in the department is done with differential equations, things like this. It's a classic SIR model. We've got susceptibles, infecteds, and resistance, and we can describe what's going on purely in terms of the rates of change. We don't know what S is at a given time, but we can tell you how it changes. And these are super useful. So the basic approach, if you've never seen one before, is we just assume we know what's going on at the moment. We know what S and I and R are now. We say, well, how are they changing? And then we move a little bit along the line, and we repeat the process, so on and so forth. The whole thing has been sort of known how to do for a very long time, and as the chair would well know, this is implemented in a package called DESolve, which I'm a huge fan of and have used since it stopped being ODESolve, right? This is how the researchers might implement a simple model. So this is a simple SIR model. I got this from some teaching resources that our people use. And you can see at the beginning of the equation, we unpack, so first of all, it's a function, I should say, just a plain old R function. It takes time, like where we are now, it takes the state, y, and it takes some parameters, which can be literally anything you want to pass to it. First, you unpack those until you've got the things that actually form your equation, the things you want to work in, and then you return the rates of change of those things with respect to time. And the first thing that sort of hits you in the face with this is that quite a lot of the body of the function is often taken up by the bookkeeping, the marshalling the data into a form where you can start connecting it back up with the mathematics, a thing that as a researcher you really deeply care about. This gets way more complicated if the things that you're pushing around aren't simple scalars, if they happen to themselves be vectors, if you're unpacking your state vector into some sort of structured format. And this leads to this sort of pattern here. This just turns up in a DESolve docs, and it works really, really well, but it is super slow, which is to use with to sort of lift everything out into an environment and then just evaluate directly on those. So it's super expressive, but particularly because these functions are called over and over and over again in these tight loops, the speed cost is quite measurable. So the DESolve authors thought about this, and they came up with a compiled code interface, which is super useful. So you can write out your same right-hand side, the same targets, in C, load them into R using its dynamic library system, and then you can work with the model purely in C code. So once you do this, you call DESolve's functions. They are themselves written in Fortran mostly, I believe, and then they call your compiled code. So nothing ends up heading back into R, there's no allocations, things are heaps faster, but you've got to write all this junk. So you've got to be much more careful about things like your parameters. The way that the DESolve authors have handled this is that they go in a global or a static object that you then unpack. And you've got 2 things that you have to just work with index. Now, not just your state, but also your parameters. There's no $beta, there's no $gamma. You just got to have like 0 and 1, and God help you if you add another one in between them, because everything's going to go to pot. And the thing, again, that really jumps out here is that the bookkeeping, all the stuff you got to do to make your differential equations work, ends up sort of really dominating the equation. And the interesting bit, the bit here that's in red, is becoming an ever smaller fraction of the problem. And if you're a computational epidemiologist, all you want to do is model AIDS or malaria, this is somewhat frustrating. Okay, so the researchers are being forced to choose between these two ways of doing the problem, expressive and fast. Okay, and they do this because the right-hand sides here are being written in a general-purpose language, either C or R. And we can make this trade-off largely go away by narrowing the domain and say, well, maybe you don't need to do anything you could do in an R function. Maybe the R function you call for your right-hand side is not going to run a linear model, and your C function is not going to call out to some other weird thing. And that's where the package that I'm going to present today comes in, a package called Odin. So the basic idea is this. The researchers are now going to write their code in a new domain-specific language called Odin. We're going to compile that to C. We're going to compile that into a DLL, and we're going to load it into R, and then we're going to continue to solve our differential equations to D-solve, because they don't break what's not broken, right? So there's already a whole pile of solvers in here. They're well tested. Okay, so what does Odin code look like? It looks an awful lot like R. So here is an example. This is the same SIR model as I showed you before, but implemented in Odin. And it's syntactically R. So this uses the same metaprogramming techniques that have been turning up more and more, where we just grab code that parses as R, and then rather than evaluating it, we're just going to work with them. We're going to use these metaprogramming techniques to generate out the code that we want. Okay, so within that block of code, there are a couple of calls here to user. These advertise to the interface that these are going to be user parameters. So rather than being concerned with like beta as the first thing, gamma as the second thing, these are just going to end up exposed in a constructor function as named arguments, and all the normal sort of R argument matching semantics go in there. Likewise, the users are no longer concerned about the order of the state vector. That's just going to be taken care of for them. Okay, so once it's been allocated, you just run it like this. This all just runs with DSolve, and you've got access to all of the DSolve solvers. So far, so good. So this is how it works. This is one of the expressions from within that model. Derivative of I, which is the number of infected people, is some function of beta, which is a parameter, S, I, and N, which are the variables in the model. N is the sum of all the different states. And this you can sort of imagine as a tree of lists of symbols. Some of the symbols are functions, some of the symbols are variables, and if you've had any computer science, this is going to immediately start looking an awful lot like Lisp, which is kind of what it is underneath the hood. And once we've got this, the problem of generating code just becomes a data cleaning problem, and we can recursively work through these syntax trees, applying a few simple rules and start very mechanically cranking out code. There's not a lot of difference between the code at the top and the code at the bottom. Here we just have to make sure that C doesn't do an integer division for us, stick a semicolon in the back, and work out where in the state vector we're going to stick this result. The number of rewrite rules that you need to be concerned with for the types of things that typically go into differential equations is relatively modest. So that part's all relatively straightforward. The bit that's not very obvious is where are these things coming from? How are we going to start reasoning about what goes in the model and how we work with it? So here, if you look closely, the derivatives are at the top, derivatives S, I, and R. And they use a variable n, or a quantity n, which is computed way down the bottom. And this is from some insights that I had working with the researchers, that when people are working with differential equations, all they're doing is sort of writing down mathematical truths. It doesn't really matter what order they happen in, because everything sort of just happens now, right? So this n has to be defined in terms of things, and we can sort of start thinking about this problem as a directed acyclic graph. Once we have that, we can start tooling around these models in lots of fun ways. So this is a graph for the S one here. You can see S and I and R going into N, and then N and beta and I as well going into the derivative. And we can start reasoning about these, and as we build up these graphs, we can say, well, okay, if we change C, what else changes through the system? And then as we expose that to the compiler, we can start working out, well, which bits do we actually need to evaluate when? And so we've broken up the model construction phase into an initial allocation, which is when the user runs the first constructor function, whenever they change the parameters, the user-defined things that control how the model is going to be evaluated, and then the initialization, the initial conditions, and the time-varying parts. And the idea being that nothing in the last two will ever allocate. All the allocations will happen at in the first two phases, which means that we can, at the cost of sort of outsourcing all this bookkeeping to the compiler, we can come up with models that are super efficient. Okay. The other thing it does is it prevents things like this. If you've got a model where everything's happening now, you can't possibly have a loop in it without having done something wrong. So the compiler will tell you, no, you can't have a cyclical dependency. And in more fun, a lot of the work that we do in the department ends up involving delay differential equations, and these have always involved an awful lot of faff with trying to work out how we unpack part of the state vector from before. So delay differential equation, things are no longer just a function of the system now, but they're also a function of the system at some previous point in the past. And dsolve exposes interfaces so we can say, okay, can you give me the value of my variables at some previous point? And you pass in, okay, I want the first, the fifth, and the ninth of them. So there's a lot of bookkeeping that needs to be done, but we can start analyzing how these are being used and generate out code that takes care of all that bookkeeping for us. So this is the code that the previous example generates, and it involves replaying a part of the graph over again based on the quantities here. So here we delayed the number of new infections by some latency period, and it sees that that involves the expression beta times s times I over n. And so it works out what's involved in computing that, pulls out just those variables and replays that part of the graph. And then the other thing that turns up a lot, as I alluded to at the beginning of these, when you're pushing around things that aren't just simple scalar quantities, and this is where these equations tend to get really large. So if you're working on a disease where there's a big where age has a large impact in how when you're infected and who you infect, then you work with age-structured populations. So rather than just having one quantity for the number of susceptibles, you have that be age-structured, and you have an aging model in there, and you have an infection model where the rates of infection depend on the ages of the infectee and the infector. Okay. So the way we've done that is we've implemented this sort of implicit array syntax where you write things like the above, where y is going to be ai plus bj, and then it's going to go through and generate really boring loops that go through the data structures that are there, iterating over them. And this was borrowed from a tool that's largely used in teaching called Berkeley Madonna, but it works super well for these models. And so this sort of approach ends up generating out of a few logical equations, systems of tens of thousands of equations. Okay, so this is where the state of things were a year or so ago when we had the syntax pretty much sorted out, and we were starting to think about tidying it up a bit. What we worked out is this became very unmaintainable very quickly, and so what we've done this year, just before release on CRAN, is to push the whole thing through an intermediate representation, which you can then tool again. So this is all written in JSON, and it gives you a huge pile of metadata that you can write other things around these models with, interrogating what are my variables, how are they working. We also, with this, picked up an ability to transpile R into R, which means it's suitable for use where installing things like RTools is a problem. And then more recently, also generating JavaScript models out so that you can use these in fully client-side web applications. And we have a proof of concept for this, and we'll be building this out next year. And for teaching, we're developing automatically generated Shiny interfaces based on this, so that given the model can tell you about all its inputs, all its outputs, you can just generate whole web interfaces with an interactive editor for it. And so we'll be trialing this out in a short course that we're running in the department this September. Okay, so this is called, all this is in a package called Odin. It's up on CRAN as of last week. And just to revisit the motivating examples on this, two of the researchers in the department, Ali Sherrod-Smith and Etty Unwin, they've been looking at malaria transmission, and they found that bed nets can be super powerful as an intervention method, but how powerful they'll be depends critically on what fraction of biting happens at night or in a day, and their models help elucidate where that geographic split happens. Charlie Whitaker has been looking at lower, and he's found that the reason why the new drugs that are being used to try this out have very variable success rate is probably because of very variable uptake rates within patients. And then Lily Giedlberg has been looking at using pre-exposure prophylaxis as treatment for preventing HIV transmission in female sex workers, has found that there's a significant but fairly modest effect, a much smaller effect than people were expecting on reducing the rate of HIV transmission. And with that, I just want to thank the MRC Center for Global Infectious Disease Analysis, where I'm based, the Bill and Melinda Gates Foundation, who fund a lot of our other work, and Arip and Sai, who've been super helpful for me throughout the last 5 years. And also just a quick plug, if this sort of thing is what turns you on, we have a position in our team. We're looking for a C++ programmer to work on individual-based models of malaria transmission. I'd love to talk to you if you are interested, or if you know anyone who's interested in that. And with that, I'd love to take any questions.
Thank you very much. Please wait for the microphone.
My question is,
Hello?
Hello.
There we go. My question is, within the Odin code block, can you call other R libraries or packages? Like, can you combine your stuff with other R libraries?
No, the whole thing works by really limiting what you can call. So no, you can't. As soon as you're calling out to another R code, you might as well just write another, just keep your model in R. If you need the functionality in those packages, that's going to be the way to go. This relies on lifting all of the code that you call into compiled code. You can write extensions to the syntax and bring those in as your own C functions, but certainly you can't call out to any complicated R package. And even if you could, that would the speed effect, the speed cost there would erase almost all the gains here.
How rich is the sort of function library that your code base supports, basically? Because you gave us kind of a simple derivative, right? And I wanted to see some more complicated functions.
Yeah, so the functions that support all the sort of normal mathematical functions that are supported in the RMath lib, pretty much. Basically, as people at work have asked for new things, we've implemented them, but we haven't had to add anything for quite a while. It certainly supports our use case. But anything that can be implemented directly in C can be pulled in.
Sorry, we mentioned RMatlib? Is that
the RMath library, the sub...
You mean a base RMath library?
Yeah, exactly.
Okay.
So it's R's mathematical functions.
But should be the functions at the C level, I think.
That's,
so.
exactly.
Yes.
I have a quick question, but it may arise simply because of a misunderstanding I have. So the question is based on the idea, I think I'm correct, you're kind of building a call tree in the form of a graph that you can then compute over.
Yes.
So relating back to a very serious question in terms of the richness of the expressions you can include in the language, in that meta language, how do you do it on an upfront computed graph or tree if you've got conditional statements?
So conditional statements are restricted to being within one line of code. So if you have a condition depending on time, depending on another variable, you just have to write that as a pure if-else statement. So y equals if whatever that else that.
So your system's quite clever and it can generate the call tree for both conditions.
Yes, exactly.
But you can't nest those. You can't
No.
nest.
Well,
right,
no,
okay.
you can nest them. You can nest them within a line, but every if statement is going to return exactly one value of the same type into the one thing. You can't say if this branch is true, then we're going to assign to y. If that branch is true, we're going to assign to z. That's not going to work.
Okay, so it's a restricted kind of
exactly
tree.
the left-hand side of the condition.
But they're still quite clever. So,
Small comment from my side. The solvers in dsolve are robust enough to handle if functions, but it's a little bit difficult because differential equations are defined to be continuous. So these hard limits are a challenge for the solver. So it takes longer. They cost computation time. So it's always better to have a soft limit, to define a function that switches from 1 to 0 in a small interval, like a monotype function. But you can do, just as a reminder. Okay, more questions? Because I have also one to the richness, because we made another package that works also on top of it, working on a matrix basis. And there we have the option to write C-level functions and have a defined mechanism to call it, and also a mechanism to call inputs, external data. Is something like this also available in your
Yeah, so both those things are available. You can call your own C functions. They can just be included, sort of a similar idea to hash include. And then for external data, it uses a package that we put on CRAN a year ago called cinterpolate, which implements constant piecewise linear or spline-based interpolation, and those can be directly called. So if you have data that varies over time, those can be directly used from the equations.
Okay. So. Oh, okay.
Hello, thank you for your talk. I'm using Stan for Bayesian analysis of differential equations. Do you think it could be combined somehow with Odin?
That's a great question. Yeah, no, we are in the process of work of scoping out how possible that would be. Now that we have this intermediate representation, this is pretty much after JavaScript at the top of the list for working out how it would fit in. So the hope would be that we could generate out code that would fit into those Stan blocks where where the differential equation part is being expressed to that, you can use all the machinery there for sure. So Odin makes it's completely agnostic about how these equations are used, much like DSolve. It just gives you a solution. Something like Stan, obviously, is far more opinionated, and we'd really like to work with that. If you're interested, I would be super happy to chat about that afterwards.